Good morning, everyone. I'm glad to make the presentation here on this conference. As it was said before, my name is Vladimir Danilov. I'm a postgraduate student, and I'm going to tell you about the results of my first year of education. So there are a lot of locomotion control algorithms, but recently model 3 reinforcement learning algorithms have been widely advanced. Yes, they have a large number of hyperparameters, a long training time, and difficulty to transition from simulation to reality, which is called the reality gap. But sometimes they can avoid disadvantages of model-based algorithms. In order to decrease sensitivity of hyperparameters and decrease training time, I decided to use PMTG architecture for my robot controller. Here is the goal of trained agent is to set the input signals for gait generators and to optimize its output signals, output values of joint angles in this situation. My contribution here was that I decided to use the gait generator based on CPG network because it allows to change stride frequency different gait patterns online and smoothly. So here you can see the block diagram of this gait generator. The first block is CPG network. It consists of 4 Hopf oscillators. Each of them is responsible for formation of a phase trajectory of each leg. The mapping function forms stride cycles based on phase signals and input parameters. I mean stride cycles for foot position of the robot. And then inverse kinematics block transform desired foot positions to desired joint angles. Here you can see the equations for each neuron. As I said, it is a Hopf oscillator. And using these equations, we can change our guide type online. We need to just change omega SW. It is a swing phase frequency. If we change lambda, we can change guide pattern. And here beta is duty factor. Here you can see the phase differences for the most common gait patterns. Here on this slide is shown output values for CPG network. These plots show a different phase for gaits from the table from the previous slide, and here you can see the smooth gait transition from walk to trot. Now let me show you the mapping function. The first part of this block is calculating base foot trajectory. So if we in stance phase, we use these equations. If we are in a swing phase, we use these equations. Next, we need to calculate sidewalk locomotion. It's quite easy. We just need to use these equations. And to make turning of the robot, we need to calculate these ones. And at the end, we should make a transition from a foot coordinate system to the robot coordinate system. Here is the simulation results of this block. Now I would tell you about simulation experiments. All of them were made in physics by bullet physical engine, and the condition of the experiments are shown here on this table. Here you can see plots obtained after different walking modes. The first one is just trot gait. Then here is gait transition from walk to trot. And here is increasing of stride frequency and stride length. The transition were made, if I'm not mistaken, from 4p to 8p. Here's the plots for changing the direction of the robot. And as you can see, it managed with such movements. And at the end, let me show you the tests in hardware. So of course, it is just a gait generator, and in the future I have to do a lot of work. But this algorithm shows that it works in real in hardware. And I can continue my developing of the controller. Thank you very much for your attention, and I will be very glad to answer your questions.
Thank you very much, Vladimir. So, any question? Nope. So, Vladimir, let me just ask you one question, please. The CPG-based Gait Generator probably would work as well with bigger robots, right? Because from what I can see, you applied to a smaller robot, but probably it should work with bigger robots. Do you think that is expandable for those kind of robots? And do you think that is difficult to adapt for those kinds of situations?
I don't think that it's very difficult, and I think it's not very difficult even to apply this algorithm to, for example, a hexapod robot. My classmate is going to adapt it in the future, and it looks like it's not very difficult.
Thank you very much once again. Thank you very much.
Thank you.